All right, so the first thing that we want to take a look at is power in a purely resistive circuit. Um, and so this is for power in a purely resistive circuit. And we're going to make some observations based on the equation that we derived a little bit earlier. The first thing to note is that for a purely resistive circuit, so suppose that you had a resistor here. And if I place a voltage with sinusoidal here, there's going to be a current here that's drawn. It's going to be purely sinusoidal. And one thing for certain that we can actually say is because of Ohm's law, it still applies to time-dependent sources. And for the sinusoids, this is V sub m times the cosine of omega t plus the phase angle. Well, that has to equal, well, the resistance times I sub m times the cosine of omega t plus its phase angle. And the only way that these two things can actually be equal, right, is if this phase angle is absolutely identical to that phase angle. Similarly, this magnitude and that magnitude must be absolutely the same. So one property of purely resistive circuits, even for ones that are being driven by sinusoidal sources, is that the phase constant for both the voltage and the current is the same. And one way to say this is that the current and voltage are in phase. Now let's take a look at the consequences that this has for the total power that we had. So the total instantaneous power that we had was the real power plus the real power times the cosine of 2 omega t minus the reactive power times the sine of 2 omega t, where the real power was the magnitude of the voltage and the current multiplied times 2 times the cosine of theta v minus theta I. Right. Similarly, for the reactive power, we have v sub m times v sub I over 2 times the sine of theta v minus theta I. But this must be true, right? So since this is a purely resistive load, since these are in phase, theta v minus theta I, well, that must be 0. And the cosine of 0 is 1. And so this term right here turns into 1, while the sine of the other term turns into 0. So for the instantaneous power, we actually have the power P times P 2 omega t. Notice that there is no reactive power whatsoever for a purely resistive load. On top of that, notice that this is actually time dependent, right? As the cosine goes through its cycle, so if you're waiting long enough, right, notice that this term has a maximum value of +1. It has a minimum value of -1. This also means that the maximum value for P, right, is P plus P, or 2P. That's the maximum value it can take on. And the minimum value that it can take on, well, if the cosine of 2 omega t is -1, then it's P minus P, and that's equal to 0. So the consequence of a purely resistive load is that the power itself is always a positive quantity, which is consistent with the idea that resistors themselves can only dissipate power. They can never generate it. They can't store it. They can only dissipate it. On top of that, one thing that's also worth noting is that if we're dealing with a sinusoidal source, right, the average power over one period, so here we're a resistive load, the average power over one period would be the integral from 0 to t, 1 over t dividing that times the power itself. So this, going back to the integral, is this one right here. Notice that this itself can actually be split into, by the properties of integrals, into this one plus this one right here. It can be shown very, very easily that this integral right here, well, that's just p times t, while the integral over here, because of the cosine term and the fact that we're integrating over one period, this will always disappear. So the average power over one cycle period is simply equal to the real power. This is, over one period, this is the actual power that's being delivered to the actual load, right? This is one of the reasons why we call it real power.